Good day, my name is LAU KAH CHUN, and my supervisors are Puan Munila and Dr. Chesta. In this video, I'm going to present my final year project with the title of Design and Implementation of Pipeline RISC Processor for Educational Purpose. For the introduction, Reduced Instruction Set Computer is a type of microprocessor that is well known and commonly be used nowadays compared to complex instruction set computer (CISC). It is because it has a better performance compared to CISC due to its simple addressing mode and instruction set. In RISC processor, there are two types of instruction execution method, which are non-pipelining and pipelining. So compared to the non-pipelining, a pipelining processor has a faster execution time and more efficiency. Due to this technique, which allow the multiple instruction execute concurrently. Additionally, RISC has a fixed length of instruction format, and that's the reason why it is easier to be pipeline compared to the CISC. Computer architecture is a popular and important subject that taught in all universities around the world. It usually delivers the introduction of basic computer structure, CPU design, I/O system, memory system, non-pipelining and pipelining concept, and so on. However, it seems like it's difficult to be mastered because there are too much of computer components that need to be understanding and memorized. For the problem statement, in Universiti Hussein, Malaysia, the subjects such as computer architecture and organization, microprocessor and microcontroller, and digital design are offered to the undergraduate student, especially electronics student. Usually, RISC architecture and pipelining concept are the main content of the subjects. However, the result and outcome of the subjects that brought to the student are less than lecturers' expectation. Students used to memorize the content of the subjects instead of deep understanding. Besides that, insufficient learning material and the use of traditional teaching material seems like the factors that cause the student lack of understanding and lose the interest about the subject. Therefore, the end of this project is to design and implement an 8-bit 5 stages pipeline RISC processor for educational purpose. The proposed pipeline processor is expected to become a new learning material for the microprocessor and microcontroller subject. The objectives of this project are to design and implement a pipeline RISC processor for educational purpose. Secondly, to simulate the functionality and performance of designer pipeline RISC processor over the non-pipeline RISC processor. The scopes of this study are: the processor will be designed, verified, and simulated using Intel Quartus Prime 20.1 Lead Edition. Secondly, the processor will be 8-bit, which means that it can operate 8-bit of data at a time, and the instruction format will be 16-bit long. Third, the number of stages of the instruction execution for the pipeline processor will be 5 stages, which are instruction fetch, instruction decode, execute, memory access, and write back. For the methodology, there are 3 types of instruction formats that used in this project. The first one is R type or register type. So this type of instruction format is for the arithmetic instruction, the logical instruction, and rotate instruction. Secondly is I type or immediate type. It is for the load, store, and move immediate instruction. And the third one is J type or so-called branch or jump type. This one is for the unconditional and conditional branch instruction. And next, so this is the instruction set that is used in the project. So here, as you can see, the instructions are load, store, move immediate, add, sub, the unconditional branch instruction, and from number 7 to number 10 is the conditional branch instruction. Following with the rotate instruction, the logical instructions, and also a non-operation instruction. Besides that, the assembler mnemonics, the RTL operation, the output, and the format of each instruction are listed out. So the pipeline processor are designed based on two architecture. First is Harvard architecture, where the instruction and the data are stored in different memory space separately with an independent bus connection, as shown in this figure. Secondly, it will be designed based on pipeline architecture as well, where there are pipeline register disk that pass in between each instruction execution stages. And for this project, since the instruction register IR and the pipeline register, both of them are responsible to hold the data that pass through it. Therefore I use the instruction register instead of the pipeline register, and I place it in between the instruction fetch stage and the instruction decode stage. Next, the components that are used in designing this pipeline processor are: first, program counter PC. Next, instruction memory IM, instruction register IR, register file RF, status register SR, data memory DM, and 4:1 multiplexer, which is used to select the data that need to be write back to the destination register based on the control signal RF marks WB. And then an arithmetic logical unit ALU, which is used to operate the addition, subtraction, the logical instruction, and two rotate instructions based on the control inputs. And last but not least is the control unit. So this is the block diagram of the control unit, and for this table it shows that the control sequence of each instruction in hexadecimal. So next, in order to simulate the functionality and performance of the designed pipeline processor over the non-pipeline processor, 5 different types of sample programs are created. For sample 1, it's used to demonstrate the load, store, move immediate, addition, and subtraction instructions. For sample 2 is to demonstrate the logical instructions add, OR, and XOR. And third instruction is to demonstrate the rotate instruction, which is the rotate right by 1 bit and rotate left by 1 bit. And next, sample 4 is used to demonstrate the unconditional branch instruction, following with the sample 5, which will demonstrate the conditional branch instruction. And here one of the conditional branch instruction, which is the branch if not equal to 0, will be demonstrated. For result and discussion, so here is the data path of the non-pipeline processor that will be used to compare with the designed pipeline processor in terms of the functionality and performance. And next, here is the data path of the 8-bit 5 stages pipeline processor that is designed. So here, as you can see, I have separated each components in different stages, and here is the instruction fetch stages, which contain PC, the program counter, instruction memory, and also the instruction register. And for the instruction decode part, it consists of register file and control unit. And for the execute stage, it consists of the ALU and also the status register. For memory access stage, it consists of data memory, and for write back stage, it consists of the 4:1 multiplexer. Next, I will show you the simulation result. So I will only show the simple program 1 simulation results for both NUM pipeline and pipeline processor, and after that, during the next part, I will show the performance comparison for both NUM pipeline and pipeline processor in terms of the CPI for all of the sample programs. So now let me recap back the instructions set of the sample 1. So here is the instructions in the sample program 1, and here is the expected result that we want to get during the simulation. Okay, now first, this is the simulation results for the NUM pipeline processor by using the simple program 1. So initially, I have initialized the memory with memory address with 0 is equals to 12, M1 is equals to 23, M2 equals to 34, M3 equals to 56, and the memory address with memory address 4 until the memory address 256 is FF. Okay, so now I have add the dot line so that it's more easier to see the complete, the clock period for an instruction to be completely executed. So now, as you can see, and for the NUM pipeline processor, an instruction will be completely executed after 3 clock cycle. And here, as you can see, this is the output of the program counter. So it shows that each instruction is executed one after one without overlapping, which indicating that this instruction execution style is same as NUM pipelining concept. Okay, next, let's see the result, whether it's correct or not. Okay, so here is the expected results, and let's see. RF means the register, so register 1 has a value of 85, so it's same as the expected result. And following with the other results, so all of the results are same as the expected result, so this indicated that the simulation result is correct. And additionally, since this sample program is start executed from 10 nanosecond until 630 nanosecond, therefore the total instruction execution time for this sample program for the NUM pipeline processor is 620 nanosecond. Next, before I show you the waveform result for the pipeline processor, I want to show you the pipeline execution of instructions. So here is the pipeline execution of instructions for the sample program 1. So during the first clock cycle, the first instruction loop is started to be fetched. During the second clock cycle, the first instruction is decoded, and at the same time, the second instruction is started to be fetched. And following with the third clock cycle, the new instruction will be started to fetch as well. And the first and the second instruction will continue to be executed. And then, additionally, during the 5th until the 10th clock cycle, each stage of the pipeline was processing a different instructions, which indicated that the pipeline was fully utilized during this clock cycle. Okay, so now here is the waveform result of simple program 1 for the pipeline processor. So here is, you can see, so this is the output of the instruction memory. So here is, you can see, during each clock cycle there will be a new instruction that started to be fetched, which means that the instruction is executed overlapping, which fulfill the instruction execution style of a pipeline processor. So now I will show you the each clock cycle result. So during the first clock cycle, the first instruction is being fetched. During the second clock cycle, the first instruction is decoded, and at the same time, the second instruction, move immediate, will started to be fetched. And next, the first instruction is in execute stages, and since it is a loop instruction, therefore nothing will be happen in these stages. And at the same time, the second instruction will be decoded, and also the new instruction, the third instruction will started to be fetched, and this style of instruction execution will be sent following up until this sample program is completely be executed. So now I will just go through the simulation result. So okay, so now let's see the final result for this simple program for the pilot processor. So as well, I put the expected results here for reference. So here, as you can see, here is the final result, final simulation result of this sample program for the pipeline processor. So as we can see, this one is same as the expected results, which indicated that it is correct. And now let's see the total instruction execution time of this sample program for the pipeline processor is 280 nanoseconds, which shows that it is lower than the non-pipeline processor. Okay, so now I will show you the performance comparison for the both non-pipeline and pipeline processor for all of the sample programs that I create. So here, as you can see, I've listed down all of the parameters for the performance comparison. So for the total number of instructions of the sample program, here is the total instruction execution time. Here is the clock period. I already initialized it in the test bench as 20 nanoseconds, and then the total number of clock cycles needed to be used to execute all of the instructions, and the CPI, which is the cycle per instructions. So all of these parameters are listed down. Okay, so CPI is a cycle per instruction, which is the average number of clock cycle required to execute an instruction. So let's see for sample program 1. So for a non-pilot processor, it has a CPI of 3.1, which means that it's required to use an average of 3.1 clock cycle to execute an instruction in sample 1. However, for the designer pipeline processor, it only required to use an average of 1.4 clock cycle to execute an instruction in sample program 1. And if we compare both of the CPIs, so it shows that the pipeline processor will have a lower CPI, which indicated that it has a better performance and a faster execution time compared to the non-pipeline for this simple program. Now let's see for the other program. Okay, so now as we can see, compared to the non-pipeline processor, the pipeline processor will have the lower CPIs for all of the simple programs. And as we can see here, when the total number of instructions in a simple program is higher, then the CPI that required for the simple program will be lower. And this result shows that the designer pipeline processor is consistent to the behavior of pipeline processor, which means that a pipeline processor will have a better performance and higher throughput than the non-pipeline processor. Next, for the last part, conclusion and recommendation. In conclusion, an 8-bit 5 stages pipeline RISC processor, which can support 16 types of instructions, is successfully designed and implemented. Its functionality and performance are simulated and compared with the non-pipeline processor by using the created sample programs. And the results shows that the designer pipeline processor has a better performance compared to the non-pipeline processor because it has lower CPIs for each of the sample program, as well as a higher throughput compared to the non-pipeline processor. Despite there are some limitations, this project still provides a valuable educational resource for microprocessor and microcontroller subject, which allows students to have a experience to perform various instruction execution, leading to gain better and deeper understanding of the computer architecture, especially pipelining concept. For future work, the designer pipeline processor can be enhanced by adding hazard unit, forward unit, and branch predictor to prevent the hazard, and for a better performance and faster instruction execution. Besides that, increasing number of instructions, increasing the instruction set speed, and modifying the RISC processor to RISC-V processor are also good optimization for the designer processor, as this can provide a more functionality and allow for more complex operations, making the pipeline processor can become more suitable for educational purpose. So that's all for my presentation. Thanks for watching this video.